So, welcome back, everybody. I just wanted to sneak in some 10 minutes with hints and some interpretations which you can make from the results you're going to get in part one. And then I'm going to give you a kind of a small hint on how you can get started with part two. So, if you now looked into the midterm, you will see that part one is essentially you bringing back to life the program which you wrote for homework number 5. But then you need to make some interpretations, because what you have a numerical tool, and you can analyze the motion of the Earth around the sun. But then you can ask yourself, what does this actually mean? So let me try to link some of the results which you will get with the analytical paper and pencil results which we got this week and the week before, so that you can actually make, or how to say, connect the dots and be able to link the analytical work with the numerical work. And this is actually one of the things which is nice with this case. We have a two-body problem which we can solve analytically and numerically, and both approaches give us some types of insights. When we combine the types of insight we get, the hope is that we can get a deeper insight about the physics. And as I said before, with the risk of repeating myself, as I said, this is a kind of professional damage when you've been teaching for something like 35 years. So the thing which you're going to see in further physics courses are potentials which are lookalikes of this potential here. So many of the interpretations you make are interpretations which you will also make in other physics courses. So let me just quickly switch to the whiteboard and show you these two things, and also remind you of the solutions to exercises, videos of the lectures, and handwritten notes which are relevant for the solution of the midterm here. But let's take a look at some of the interpretations which you're going to make and how you can link them with the analytical work which we've been doing. So let me switch to the whiteboard a little bit. So I hope not to take more than 10 minutes. So one of the things you have in one of the first exercises is a question about why do we expect that the kinetic energy and the potential energy are conserved independently as a function of time. So when you calculate for the circular motion, one of the things you're going to see is that the kinetic energy stays constant and the potential energy stays constant. Has any one of you seen that already? Goody. Have you thought why this is the case? Any good suggestions? So this is actually something which allows us now to make the connection with the paper and pencil exercises, or all these exercises which led to the analytical solutions. So let me try to explain to you why the kinetic energy and the potential energy are conserved, each of them. Each of them are conserved. This is not the case when you look at an elliptic motion or hyperbolic motion. And you can actually extract this kind of insight by looking at the analytical solutions. And you could have seen that without having done any calculations, or rather using the solution to the analytical solutions, right? So that means that you would have done some calculations. But let's take a look at it and remind ourselves briefly about the type of solution which we have. So what we had, so this is back to why we find that the kinetic energy and the potential energy are independent of time. So if you now look at the case the equation which we have been solving of d of r plus L squared divided by mu times r cubed. So L is a constant. And what we found is that when we plotted this potential, effective potential, let me quickly remind you of these things, as a function of the relative distance, when we looked at the case for circular motion, we found that this R min, on Wednesday, we did that by taking the derivative of the effective potential and require that derivative to be equal to 0. So this is this specific point here. We require that this dV effective of d of r is equal to 0. That is the same as minus the force, which again is the same as minus mu times r dot. Okay, so these are equations which we have been solving. So that means that the acceleration, the radial acceleration, is 0. This r min, when we did the calculations on Wednesday, we found that that was equal to L squared divided by the reduced mass times the parameter which contains all the constants in the potential. So the potential is given by this minus alpha divided by r. Now, one of the things which we also found is that the angular velocity, d phi dt, is a constant if r is a constant. And this is now given by r is equal to r min. So if we have circular motion, one of the things we found is that the radius is constant, right? We found that the angular velocity is a constant. If we now go back to the kinetic energy, so let's look at the kinetic energy, the expression which we derived in polar coordinates was given by mu of r dot squared plus 1/2 of r squared of phi dot squared. So if we are at r equal to r min, and that's a constant, what happens with the kinetic energy as a function of time when you just look at this equation here? It's a constant. The radius is a constant, right? It's a circle. The angular velocity, d phi dt, is a constant. But what about the radial velocity, dr dt? So we have a term here which goes like r dot squared. What about that one? I didn't say anything about it, but we mentioned in the lectures when we did the derivations that this took a specific value. So remember, r is constant, the radius is constant. What should the derivative of the radius be then? 0, right? So it means that the first term in the kinetic energy is 0. The only term which now gives us a contribution to the kinetic energy is the one with r squared. R is a constant. This guy here is a constant because the angular velocity is a constant, as we have shown when we have a central force. So it means that the kinetic energy here has to be a constant. So when you calculate the kinetic energy as a function of time, you're just going to get a flat line. And that's the way it should be for circular motion. Now, when you go to elliptical motion, that means that what we have is the following. So if we now go back to the figure here, then what we did was to place ourselves here. So we had a minimum value and we had a maximum value. So we got, and now I can change colors here. So we had an R min here, and then we had an R max. And their values were given by this constant of 1 plus epsilon, and epsilon is positive, and C divided 1 minus epsilon. Now, if you look at the expression for the potential energy, which you have here, if you now just look at this expression here, what would you expect if you now have elliptical motion about the potential energy? Is that going to be a flat line as a function of time? Or will it not? What's your feeling? Excellent. Did everybody hear that? Sometimes I have some hearing problems because I have this pods here, so it gets a little bit. So when I hear you guys, I'm not sure if everybody hears it. Sorry for that. But you see now immediately, since these values are C of 1 minus epsilon, and when you go from this point to the other one, this is going to change. So the potential energy is going to fluctuate. And that means also that if we look at the kinetic energy again, if we look at that one, that's also going to fluctuate. So what you will see now is that the kinetic and the potential energy for an elliptical orbit is just going to go up and down between a minimum and max value. What should the total energy be? What about the total energy as a function of time? What would you expect now? So we have been talking about conservative forces, right? Yeah, it should be a constant. So the total energy is a constant. So if you go beyond a circular motion, which is a very special case, then the total energy is conserved, but the kinetic and potential energy by themselves, they will oscillate between maximum and minimum values. And this is what you're going to see. Now, there's another exercise which deals with Kepler's second law, which says that when an object is orbiting around the center, then what you're going to have is that the area which it spans is going to be a constant of time, irrespective of where you are. Now, this means that if you now go to section 3.4 of Taylor, what you will see then is that there is an expression here, and this expression simply says that the derivative of this area, dA of dt, you can show that this is given by the angular momentum divided by 2 times m. And this is the same as 1 divided by 2m. And then what you have is r cross p, this is a cross product. And we know that p, the momentum, is, so sorry, this should not be m, it should be mu. This is just given by mu times the velocity. So if you plug that one in, it means that this quantity, the angular momentum, divided by 2 mu, we can drop 2 mu, so that is 1 over 2, and then I have a mu here, so I get 2, and it is r times v. Now, if you want to show that angular momentum is conserved as a function of time, how would you do that numerically or in your program? So you have a lovely program which gives you velocities and positions. So how would you demo? Yeah? Yeah. Exactly. So, did everybody hear that? Excellent. This is an excellent answer. So what you have these objects as function of time, right? So when you've done the calculations, you have an array with positions and one with velocities. And then you simply calculate another time-dependent array, which is the cross product of the two. And if that is flat again, then you have shown that angular momentum is conserved. How many have reached that stage? So somebody has done it already? Not yet. So I just wanted to discuss these things with you. So it sounds a little bit strange that it's not giving you the solutions because you have to do it and see it, but it's more to guide your eye so that you can link what you have developed numerically, the calculations you run, with what we see from the paper and pencil exercises and what you see in chapter 8 in Taylor. So hopefully then you can see this kind of mix of numerical calculations, analytical calculations, and that is how a physicist or a scientist normally works. So you have some numerical tools, but then you have to ask yourself, do these results make sense? And we are pretty lucky in this case because we have numeric analytical solutions. And then we can go back to these and say that, okay, this fundamental law of nature has all these nice features. And we see that. Okay, so the last thing I want to sneak in is how do we deal with Jupiter? So let's just do that, and then we continue solving exercises. Any questions? I mean, things which are unclear? Okay, let's look at the Jupiter case. And that's the last thing I'm going to do. So what we have then, we now include Jupiter, is that we need to define the position of Jupiter, obviously. So this is for part 2, and get you started with that one. You will find the video online afterwards, and you will also find these notes. So we know that the mass of Jupiter is something like 1.9 times 10 to the 27th kilogram. So it's roughly 1,000 times lighter than the Earth. If we look at the force between Earth and Jupiter, so now so E for Earth and J for Jupiter. And if we look at the X component, this is going to be given by minus G times the mass of Jupiter times the mass of Earth. So be careful then, because there's another force which acts on Jupiter from Earth, which has the same expression, but it has the opposite sign. That's Newton's third law, right? So then what we have is the distance, the X component of the distance between Earth and Jupiter. And then we have the radius between Earth and Jupiter cubed. And this xej is going to be given by the distance between the Earth and Jupiter. So you just have to be careful with the way you define these distances, because that has importance for the way the coordinates and the forces come out in your code. And if you stay just in 2 dimensions, this is given by xj minus xe squared, and then ye minus yj squared. So you can run this in 3 dimensions, as we discussed on Wednesday. This means also that the force we have now, F of E Jupiter of x, divided by the mass of the Earth, so this is the acceleration which we need to plug into the code. This is the same as the velocity of Earth, the x component of dt. So this is the velocity of the acceleration which it gets from the interaction with Jupiter. And that's given by minus g times m. And then we have this distance. So this is multiplied. Oh, sorry, just a moment. This is not what I wanted to show you. Let's write the total force on Earth and its x component. And that is given by the velocity for Earth in the x direction of dt. It has a contribution from the sun, which is given by this one, multiplied with the Earth, divided by the distance from the Earth to the sun, cubed. But then I need to add the contribution from Jupiter. And you would have to do the same thing when you now include Jupiter. So that's going to have a contribution from the sun and a contribution from the Earth. So this is given by xe minus xj. And you have a similar one for the y direction. If you wish to go in 3 dimensions, you would have a similar one for the c directions. So that means that what you would need to plug in for the y direction, you would have a y of e minus y of j. Similarly, you would have the y position, and you need the c position as well. So I'm not setting up the positions, the forces in the x, in the z and the y direction, because they look very much similar to the one in the x direction. So when you're starting with part 2, this is the piece you would need to add to the acceleration. So this is your new acceleration in part 2. Now, one of the things which we did in homework 5 was that we introduced atomic units. So we changed G times the mass of the sun to be equal to 4 pi squared in terms of 1 astronomical unit squared, or cubed actually, cubed divided by 1 year squared. So these were our new units when we run the calculations in homework number 5. Now you should feel free to not do that. You can introduce the real masses and the other constants, but then you just have to be a little bit careful with the way you define your time steps, because you shouldn't do your time steps in seconds, because you're interested in simulating the system for many years. Now, if you look at what we have now with Jupiter, is that we have the mass of Jupiter, and this doesn't look like the gravitational constant times the mass of the sun. So what's the simplest way of introducing this 4 pi square term? So this is actually the trick you need to do when you're scaling your equations here. So what's the simplest possible way? You could actually introduce this factor 4 pi squared. Any good ideas? So I like this 4 pi squared, and I want to bring it back again into all the planets, in the equations for all the planets. So there's a famous number. Yeah. Go ahead. No, go ahead. That's the way you would proceed. So you just introduce number 1, and which is now equal to mass of the sun divided by mass of the sun. And then the only thing you need to deal with then, so if we now look at this specific term, so if you look at this term here, what you do now is that in here you multiply with 1, and 1 is simply equal, so this is 1, the mass of the sun divided by the mass of the sun. Right? So then we can bring it back 4 pi squared, but we have to be careful then, because we will need to scale this equation with the mass of Jupiter divided by the mass of the sun. So the way that equation is going to look like, if we do this, we are going to get that this equation now is equal. So the acceleration for the Earth in the x direction is going to be equal to minus 4 pi squared. The distance in the x direction from the Earth to the Sun divided by the distance to the Sun, which is 1 astronomical unit, minus 4 pi squared. But now we have a mass of Jupiter divided by the mass of the Sun. And this is multiplied with the distance in the x direction between Jupiter and the Earth, and the radius cubed. So these are the things which you need to add to your code from part 1. And then when you move to part 2, you need this addition here, in the x direction, in the y direction. And then you should be able to simulate a three-body system. And adding the other planets is simply you adding more and more forces. Okay, I'm going to stop here now. So George will follow you guys online, and Julie and I, we will just walk around here, and we are going to hang around at least to 5 o'clock, if you wish to hang around. So I'm going to switch off the recording. You will find the recording online afterwards, and same with the notes here. Any questions so far, before we switch off the machinery here?